Alright, this problem says a converging lens with a focal length of 17.5 centimeters is located 8.74 centimeters to the left of a diverging lens, and that diverging lens has a focal length of negative 10.4 centimeters. Now let's say we have an object 47.4 centimeters to the left of the converging lens. Can we find the final image that's formed by this lens combination? Alright, so over here I put an object that's just 10 centimeters tall. This is going to be our converging lens here. And then to the right of that we'll have our diverging lens 2. Alright, I want to put the focal points down first of all. So we have to go 17.5 centimeters to the left of our converging lens and 17.5 centimeters to the right of it. So that's right about here. We also have to go 10.4 centimeters to the left of the diverging lens. I believe that'll be right about here. And perhaps here. Okay, let's draw some rays. Alright, one of the first rays to try here would just be the parallel ray, parallel with the principal axis. Okay, now since this is a converging lens, that ray would be bent toward focal point 1. Okay. We would also send a ray straight through the center of that lens. And we might as well draw this ray as well. Okay, we can clearly see where the image for that first lens is going to be formed. Right there. But once again, this is going to be a virtual image, because rays will never get the chance to go to that location. So where will they actually go? Well, check out the parallel ray, the one that comes out parallel. That ray is headed into a diverging lens. But we know what happens when parallel rays come into a diverging lens. They'll want to diverge from the focal point of that lens. So what I want to do is start from the focal point F2 and I want to let that ray which is coming in parallel there, It's going to diverge. So it ends up going that way. Okay. So that gives us one ray that would be like a final ray for our final image. But so far, that's all I have. So what else could I come up with? Well, you could do this. A ray which connects with the virtual image. One of them would have to pass through the focal point F2. And then the way that that ray had got there, according to the virtual image construction, would have been like this. Okay, now that's what it would have looked like if the diverging lens wasn't there at all. That's what we would have had, right? But that ray is going to hit the diverging lens and its path is going to change. But how will it change? Well, it's coming in through the focal point, which means it will actually come out parallel when it hits that diverging lens. It'll come out like this. All right. Now what we can do is we can trace those rays back to where they apparently would have came from. So if you're looking at the situation from the right side of the screen here, then you would think that that ray had actually come from the left side. You would think that it came from back here. So what I'm sketching now is just the apparent source of the rays. And I want to do one more for this ray here. So where they appear to come from is actually somewhere back here. Now it's possible my drawing could be just slightly, skewed a little bit. So maybe I'll draw a third ray as well. Another ray we can draw would be one which approaches the image here and goes through the center of the diverging. Okay, but if it did that, it wouldn't be bent. So this ray would be an important one, and as you can see, it extends back to touch the final image as well. All right, so yeah, we might be right about there. with our final image. Let's see if I can straighten it out a little. There we go. That's the construction. So this would be our final virtual upright image. All right, the last thing to do is just see if the mathematics agree with this picture. Okay, let's try the formulas. So we'll do a thin lens formula for lens 1. 1 over DO1 plus 1 over DI1 equals 1 over F1. Alright, they said it was 47.4 centimeters away from lens 1. And a focal length of 17.5 centimeters. The image location is 27.7 centimeters. Okay, so we're talking about this distance. It's 47.4. And then this distance here is apparently 27.7. That is DI1. Alright, that looks about right. Now we want to find the object distance for lens 2. So we'll do DI1 plus DO2 equals the lens separation. The lens separation is 8.74 centimeters, they had said. Alright, so we'll do 27.7 plus DO2 equals 8.74. I'm getting negative 19 centimeters. Next, we'll do thin lens formula. For lens 2. So 1 over DO2 plus 1 over DI2 equals 1 over F2. One over negative 19 plus 1 over DI2 equals 1 over negative 10.4. This is a diverging lens. Yeah, we have to use a negative focal length. And I get a final answer of di2 equals negative 23 centimeters. Now the convention for lenses is if the image comes out positive, then it comes out on the opposite side of the object. But if the image distance comes out negative, it ends up being on the same side as the original object. And so that would be the case here in our problem. Yeah, in our problem, it looks like our final is di2 equals negative 23 centimeters, which means 23 centimeters in front of lens 2. And it does look correct. All right, lastly, we'll just find the magnification of it. M1 times M2, negative di1 over do1 times negative di2 over do2. So 27.7 over 47.4, negative 23 over negative 19. I get 0.71 for the magnification. And that looks about right. Could be 71% of the original height. I made the original height 10 centimeters. So let's find the height of that image. There we go.